All right, let's break down the concepts of heat and temperature in the simplest way possible. I'll explain each part step by step using easy language. 1. What is heat? Heat is a type of energy. Think of it like the energy that warms you up when you sit by a fire. Imagine you have a cup of hot chocolate. The heat is the energy that makes the chocolate warm. Heat is all the energy inside something that makes it feel warm or hot. Part 2. What is temperature? Temperature is a way to measure how hot or cold something is. If you touch a warm cup and a cold ice cream, you can feel the difference. The warm cup has a higher temperature, and the cold ice cream has a lower temperature. Think of temperature as a number that tells us how hot or cold something is. Higher numbers mean hotter. Lower numbers mean colder. 3. Difference between heat and temperature. Heat is about the total energy. It tells us how much energy is there to make something hot. Temperature is about the average energy of particles in something. It tells us how hot it feels. Example to understand. Imagine two things: a small cup of boiling water and a big pot of boiling water. Both are boiling, so both have the same temperature. But the big pot has more water and therefore more heat. Even though both feel equally hot, same temperature, the big pot can keep things hot for longer because it has more heat. 4. How does heat move? Heat always moves from hotter things to colder things. For example, if you put an ice cube in your warm hand, heat moves from your warm hand hotter to the ice cube colder. This is why the ice melts. Your hand loses some heat and the ice gains it. Part 5. Why do we feel temperature? We feel temperature because of how fast the tiny particles, called molecules, inside things are moving. When something is hot, its molecules move fast. When something is cold, its molecules move slowly. 6. Molecular motion and heat. Every object is made of tiny particles called molecules, which are always moving. If you heat something, these molecules move faster. When molecules move faster, they bump into each other more, creating more heat. 7. Temperature and molecular motion. Temperature measures the average speed of these moving molecules. If the molecules in a cup of water are moving very fast, the temperature is high. If they are moving slowly, the temperature is low. 8. Simple experiment to understand heat and temperature. Take two cups, one with a small amount of warm water, one with a large amount of warm water. Both might feel warm, same temperature, but if you pour both into separate bowls of cold water, the bowl with the large amount of warm water will warm up more because it has more heat to give. 9. Important points to remember. Heat is the energy in things that makes them feel warm or hot. Temperature is the measure of how hot or cold something is. Heat flows from hot to cold. The faster the molecules move, the hotter the temperature. The more molecules moving fast, the more heat an object has. Summary. Imagine heat as the total amount of warmth energy and temperature as the level of warmth or coolness. A large pot of hot soup has more heat than a small cup of hot soup, even if they both are at the same temperature. By understanding these basic ideas, you can start to see how heat and temperature affect the world around us. Sure, let's break down radiation even further and make it as simple as possible. What is radiation? Radiation is a way heat moves from one place to another without needing anything to carry it. It's like the way sunlight travels through space. Imagine you're outside on a sunny day. You can feel the warmth from the sun even though there's nothing in space, like air or water, between you and the sun. How does radiation work? Energy and waves. Radiation moves in the form of invisible waves. Think of these waves like ripples you see when you drop a stone in water, but these waves move through space instead of water. Example: when you stand in sunlight, you feel warm because the sun's energy travels through the empty space of the vacuum, where there's nothing, and reaches you. How is energy radiated? All objects radiate energy. Everything around us, like your hand or a heater, gives off some energy as radiation. Temperature matters. The hotter something is, the more energy it radiates. For example, a hot stove radiates a lot of heat. A cold cup doesn't radiate much heat. Why? Hot things have more energy, so they send out more heat in the form of radiation. Transparency to radiation. Transparent materials. Some materials allow radiation to pass through them. These materials are said to be transparent to radiation. Example, glass windows. They let sunlight radiation pass through them so you can see outside. At the same time, they keep the heat from escaping inside, so your room stays warm. Why? Glass is like a clear window for radiation, allowing light and heat to come in, but keeping the warmth from escaping. In summary, radiation is how heat moves without needing anything to carry it, like through empty space. It travels in invisible waves. Everything that's hot radiates energy, and hotter things radiate more energy. Materials like glass let radiation pass through, which is why they can keep your house warm by letting in sunlight, but keeping heat inside. I hope the radiation easier to understand. Let's break down conduction and convection in simple terms. What is conduction? Conduction is how heat moves through a material by making its particles, like atoms or molecules, bump into each other. It happens when two parts of an object or two different objects that are touching each other have different temperatures. How does conduction work? 1. Heat movement. Heat always flows from the warmer part to the cooler part of a material. 2. Molecular activity. The particles in the warmer part move faster and bump into the particles in the cooler part, passing on the heat. Examples. Metal spoon in hot soup. When you put a metal spoon in hot soup, the part of the spoon in the soup gets warm first. The heat then moves through the spoon to the handle. Why? Metal conducts heat well because its particles transfer energy easily. Why is conduction less important for weather? Limited impact. In the atmosphere, the difference in temperature between the ground and the air is usually not huge, so conduction isn't very effective for heating or cooling the whole atmosphere. Example, on a cold winter night, the air just above the ground might be cold, but the effect doesn't go very high because conduction isn't strong enough to heat the whole atmosphere. Convection. What is convection? Convection is how heat moves by the actual movement of a fluid, liquid or gas, from one place to another. It happens because fluids, like water and air, can move around, carrying heat with them. How does convection work? 1. Heat movement. When a fluid is heated, it becomes less dense and rises. Cooler, denser fluid moves in to replace it. 2. Mass motion. This movement creates a flow that helps spread the heat around. Examples. Boiling water. In a pot of boiling water, the hot water at the bottom rises, and cooler water at the top sinks down to be heated. This movement helps evenly distribute the heat. Weather patterns. Warm air rises near the ground, and cooler air moves in to replace it, creating winds and affecting weather. Why is convection important? Effective heat transfer. Convection is crucial for moving heat around in fluids and gases, like in oceans, the atmosphere, and even in the heating of your home. Example. When you use a fan in a room, it helps move warm air around, making the room feel more evenly warm. Summary. Conduction. Heat moves through direct contact between particles and solids. Metals conduct heat well, while air does not. Convection. Heat moves through fluids, liquids, and gases by the movement of the fluid itself, spreading heat more effectively in these substances. Both conduction and convection are important for different ways heat is transferred in our world. Here's a simple breakdown of how the atmosphere gets heated and cooled based on different processes. 1. Partial absorption of solar radiation by the atmosphere. What happens? When sunlight reaches Earth, some of it is absorbed by the atmosphere before it even reaches the ground. This absorbed energy warms up the atmosphere directly. Example, just as you feel warmer when the sun is shining, the atmosphere also absorbs some of this solar energy. 2. Conduction. What happens? Heat is transferred from the Earth's surface to the air in contact with it through conduction. The air just above the ground gets warmed up because it touches the warm ground. Example, on a sunny day, the ground heats up and the air in contact with the ground gets warmer. 3. Terrestrial radiation. What happens? The Earth's surface absorbs solar energy and then radiates some of this energy back into the atmosphere as heat. This process helps warm the atmosphere. Example, at night, the Earth cools down and radiates heat back into the atmosphere, which can still warm the air. 4. Convection and advection. What happens? Convection. Warm air rises and cool air sinks, creating a cycle that helps distribute heat in the atmosphere. Advection. This is the horizontal movement of warm or cold air across different areas, affecting local temperatures. Example, a breeze you feel on a hot day is a result of warm air moving away from the ground and cooler air moving in. 5. Latent heat of condensation. What happens? When water vapor in the air condenses into clouds, it releases heat, latent heat, into the atmosphere. This process helps warm the air. Example, when you see clouds forming, the process of condensation releases heat that warms the surrounding air. 6. Expansion and compression of the air. What happens? Expansion. When air rises, it expands and cools down. Compression. When air descends, it compresses and warms up. Example, when air rises in the atmosphere, it expands and cools, which can lead to cloud formation. Conversely, descending air gets compressed and warms up. Summary. Solar radiation. Some of the sun's energy warms the atmosphere directly. Conduction. Heat moves from the ground to the air in contact with it. Terrestrial radiation. The Earth radiates heat back into the atmosphere. Convection and advection. Warm air rises and cool air sinks, moving heat around. Latent heat. Condensation of water vapor releases heat into the atmosphere. Expansion and compression. Moving air cools or warms based on its movement. These processes work to continuously heat and cool the atmosphere, affecting our weather and climate. Let's simplify the explanations of partial absorption of solar radiation and conduction. 1. Partial absorption of solar radiation. What happens? When sunlight reaches Earth, not all of it goes straight to the ground. Some of it is absorbed by dust particles and water vapor in the lower layers of the atmosphere. About 10% of the incoming solar energy is absorbed by these particles. Most of this absorption, about 50%, happens in the lower 2 kilometers of the atmosphere, where there is a lot of water vapor. Why it matters? While this absorption does warm the atmosphere slightly, it doesn't significantly raise the temperature at the Earth's surface. On sunny days, even though the sun is shining, the temperature at the surface can still be low because the atmosphere only absorbs a small part of the sun's energy. Example, in winter, you might sit near a sunny wall to stay warm. The wall absorbs sunlight and then radiates heat, long-wave energy, that helps warm you up. 2. Conduction. What happens? Conduction is the transfer of heat through direct contact. It happens slowly, especially in air. Since air is a poor conductor of heat, conduction mainly affects only the very bottom layer of air close to the Earth's surface. Why it matters? Because air doesn't transfer heat very effectively, conduction is not very important for heating or cooling the atmosphere as a whole. Most weather changes in atmospheric temperatures are not significantly influenced by conduction. Example, if you touch a cold metal object, the heat from your hand moves into the metal, conducts. However, in the atmosphere, this process is so slow and limited to the lowest layer that it doesn't have a big impact on overall weather. Partial absorption of solar radiation. Some sunlight is absorbed by particles in the lower atmosphere, but this doesn't greatly affect surface temperatures. Conduction. Heat moves slowly through air, affecting only the air closest to the ground, and is not very important for overall atmospheric heating. These processes are part of how the atmosphere interacts with heat, but they are not the main drivers of weather changes. Here's a simplified explanation of terrestrial radiation and how it affects the atmosphere. Terrestrial radiation. What is it? After the Earth absorbs solar energy, it converts this energy into heat, which is then radiated back into the atmosphere as long-wave infrared radiation. This process is called terrestrial radiation. How does it work? During the day, the Earth absorbs more solar energy than it radiates. At night, the Earth loses heat through terrestrial radiation. The Earth radiates heat like a black body, meaning it emits energy in all directions. This is different from the atmosphere, which only absorbs certain wavelengths of radiation. Atmosphere's role. Most atmospheric gases, like carbon dioxide and water vapor, absorb a significant amount of the Earth's long-wave radiation. For example, water vapor absorbs about 85% of this radiation, helping to trap heat in the atmosphere. The atmosphere is almost transparent to short-wave solar radiation, but absorbs long-wave terrestrial radiation effectively. This helps keep the Earth's heat from escaping too quickly. Greenhouse effect. This trapping of heat by the atmosphere is known as the greenhouse effect. It keeps the Earth's surface warmer by preventing heat from escaping into space too quickly. Day and night effects. During the day, the Earth's surface heats up and radiates heat, but this heat is not immediately lost because the atmosphere absorbs and re-radiates it. At night, without the sun's energy, the Earth loses heat through radiation, and the atmosphere helps to keep the temperature from dropping too rapidly by absorbing and re-radiating some of this heat. Role of water vapor in clouds. Water vapor, it is very effective at absorbing terrestrial radiation, making nights warmer in places with high humidity. Clouds. They also trap heat. Cloudy nights are warmer because clouds absorb and re-radiate heat more effectively than clear skies. Temperature changes with altitude. The Earth's surface radiates heat to the air, which then radiates heat both upwards and downwards. This causes a gradual decrease in temperature with higher altitude. Balance of energy. The Earth receives energy from the sun and radiates an equal amount of heat back into space. The atmosphere plays a key role in balancing this energy by absorbing and re-radiating heat. Summary. Terrestrial radiation. After absorbing solar energy, the Earth radiates heat as long-wave infrared radiation. Atmospheric absorption. The atmosphere absorbs this radiation, which helps to keep the planet warm. Greenhouse effect. This process of trapping heat is known as the greenhouse effect. Day versus night. The atmosphere helps to balance temperatures by absorbing and re-radiating heat during the day and night. This balance between incoming solar radiation and outgoing radiation is crucial for maintaining the Earth's climate. Latent heat of condensation, how it heats and cools the atmosphere. To understand how the atmosphere gets heated or cooled, we need to learn about latent heat, a hidden form of heat energy that's very important for the weather. What is latent heat? Latent heat is the heat energy absorbed or released when water changes its state, like from liquid to gas or from gas to liquid, without changing temperature. Latent heat of evaporation. This is the heat absorbed when water evaporates, turns from liquid to gas. Latent heat of condensation. This is the heat released when water vapor condenses, turns from gas to liquid. How does this heat the atmosphere? 1. Evaporation, the storage of heat. Water bodies and evaporation. Large water surfaces like oceans absorb heat from the sun. When the sun shines, it heats the surface water of oceans, lakes, and other bodies of water. This heat causes water to evaporate, turn from liquid into vapor. Energy absorption. During evaporation, water absorbs a lot of heat. This heat energy is used to break the bonds between water molecules, turning them into vapor. This heat energy becomes latent heat because it is hidden inside the water vapor. It doesn't raise the temperature of the vapor. 2. Condensation, the release of heat. Cooling and condensation. When warm, moist air rises, it cools as it gets higher in the atmosphere. As the air cools, the water vapor in it begins to condense back into tiny water droplets, like those in clouds. Heat release. When condensation happens, the latent heat stored in the water vapor is released back into the air. This released heat warms the surrounding air. Heating the atmosphere. This process adds heat to the atmosphere, especially in the middle and upper layers of the troposphere. the lowest part of the atmosphere where weather happens. Why is latent heat important for weather? Cloud and storm formation. When warm, moist air rises and cools, it can lead to cloud formation. The release of latent heat during condensation warms the air, making it rise even further, which can lead to strong weather patterns like thunderstorms and hurricanes. Temperature regulation. The release and absorption of latent heat help regulate the temperature of the atmosphere. It balances out the temperature differences, preventing extreme hot or cold conditions. An example of latent heat in action. Oceans as a heat source. Imagine the ocean as a huge heat store. On a sunny day, a lot of solar energy goes into evaporating water from the ocean surface. This process stores heat in the water vapor. When this water vapor moves up and cools in the atmosphere, it condenses into clouds and releases heat. Nighttime cooling. At night, without the sun, the air cools down, causing more condensation. This condensation releases latent heat, which can keep temperatures from dropping too much, especially on cloudy nights. Key points to remember. Latent heat is hidden heat energy stored when water evaporates and released when water vapor condenses. Condensation of water vapor releases heat into the atmosphere, warming it. Evaporation absorbs heat from the surroundings, cooling the area it happens in. This process helps regulate atmospheric temperatures, form clouds, and drive weather patterns. By understanding latent heat, we can better understand how the atmosphere stays warm, how weather systems form, and why precipitation happens. Expansion and compression of air, understanding adiabatic processes. To understand how air heats up and cools down as it moves up and down in the atmosphere, let's learn about adiabatic processes. This might sound like a big word, but don't worry, we'll break it down step by step. What is adiabatic heating and cooling? Adiabatic means there's a change in temperature of air without any heat being added or taken away from it. The temperature changes happen because of changes in air pressure. Adiabatic cooling. When air rises, it moves into areas where the air pressure is lower. As it rises higher, the pressure keeps dropping. With less pressure, the air expands. When the air expands, it cools down. This cooling process is called adiabatic cooling. Adiabatic heating. When air sinks, comes down, it moves into areas where the air pressure is higher. As it goes lower, the pressure increases. With more pressure, the air compresses, gets squeezed. When the air compresses, it heats up. This heating process is called adiabatic heating. How does adiabatic cooling and heating work? 1. Rising air and cooling. Imagine a hot air balloon. As it goes up in the sky, the air around it gets thinner and has lower pressure. The air inside the balloon expands because there is less pressure pushing on it. As the air expands, it loses energy and cools down. This is why the temperature gets colder as you go higher up in the mountains. The air is expanding and cooling down adiabatically. 2. Sinking air and heating. Now think of air coming down from a mountaintop. As it goes lower, it enters areas with higher pressure. The air is squeezed or compressed by this pressure. When the air compresses, it gains energy and heats up. This is why the air feels warmer in valleys compared to higher elevations. The air is compressing and warming up adiabatically. Why is this important for weather? Cloud formation. When warm air rises, it cools down adiabatically. If it cools enough, water vapor in the air can condense into tiny water droplets, forming clouds. If the air continues to rise and cool, it might even rain. Weather patterns. Understanding how air heats and cools as it moves helps meteorologists predict weather patterns like thunderstorms, cold fronts, and warm fronts. Controls of temperature. What affects temperature on Earth? The temperature at a place on Earth depends on several factors. 1. Latitude. Places closer to the equator, like Brazil or Kenya, are warmer because they receive more direct sunlight year-round. Places closer to the poles, like Canada or Russia, are colder because they receive less direct sunlight, especially in winter. 2. Altitude. The higher you go above sea level, the cooler it gets. For example, the top of Mount Everest is much colder than the base because of adiabatic cooling. 3. Distribution of land and water. Land heats up and cools down faster than water. So coastal areas like Los Angeles have milder temperatures, while areas far from the ocean like Las Vegas have more extreme temperatures. 4. Ocean currents. Warm currents, like the Gulf Stream in the Atlantic Ocean, bring warm water and air to nearby regions, making them warmer. Cold currents, like the California Current, can cool down coastal areas. 5. Prevailing winds. Winds that blow from the ocean often bring moist, mild air, while winds from the land can bring dry, hot, or cold air depending on the region. 6. Cloudiness. Clouds can block sunlight during the day, keeping temperatures cooler. At night, clouds can trap heat, keeping temperatures warmer. 7. Mountain barriers. Mountains can block winds and create different climates on each side. One side may be wet and cool, while the other is dry and warm, like in rain shadows. 8. Nature of the surface. Dark surfaces like forests absorb more heat, while light surfaces like snow reflect more heat. This affects how warm or cold an area gets. 9. Relief and convection. Relief refers to the shape of the land. Valleys, plains, and mountains affect local temperatures. Convection is the upward movement of warm air and the downward movement of cooler air, redistributing heat. 10. Turbulence. Turbulent mixing in the atmosphere helps distribute heat. For example, strong winds can mix warm and cold air, affecting temperatures. Additional information. Why does the temperature drop with altitude? This happens because as air rises, it expands and cools due to lower pressure, adiabatic cooling. This is why mountaintops are always colder than the valleys below. What causes wind? Wind is caused by air moving from high-pressure areas to low-pressure areas. When the sun heats the earth unevenly, it creates high and low-pressure areas. The air moves to balance these differences, creating wind. By understanding these basic principles, we can better predict and understand weather patterns and climate behavior. This is how meteorologists forecast the weather, helping us different weather conditions. Latitude and temperature. How does latitude affect Earth's temperature? To understand how temperature changes across the Earth, let's start with the concept of latitude and how it affects the insolation, the sunlight that reaches the Earth's surface. What is latitude? Latitude is a way to describe a location's position on Earth in relation to the equator. The equator is an imaginary line that runs around the middle of the Earth, like a belt. It is at 0 degrees latitude. Latitudes are measured in degrees. Places north of the equator have north latitude, 0 degrees to 90 degrees N, and places south of the equator have south latitude, 0 degrees to 90. What is insolation? Insolation stands for incoming solar radiation. It is the amount of the sun's energy that reaches the Earth's surface. Insolation is like the sunlight that warms the Earth. How does latitude affect insolation? 1. Intensity of sunlight. The intensity of insolation, how strong the sunlight is, depends on the latitude of a place. Near the equator, sunlight hits the Earth more directly. Think of it like a flashlight shining straight down. The light is focused and strong. Near the poles, sunlight hits the Earth at a slant, spreading out over a larger area. This is like a flashlight shining at an angle. The light is less focused and weaker. 2. Temperature and latitude. Because the equator receives more direct sunlight year-round, it is generally warmer there. This is why countries near the equator, like Brazil or Kenya, have warm climates. As you move away from the equator towards the poles, north or south, the sunlight becomes less direct, and the temperature gets colder. This is why places like Canada and Russia, which are closer to the poles, are colder. 3. Seasonal changes. The Earth is tilted on its axis, which means that as it orbits the sun, different parts of the Earth receive more direct sunlight at different times of the year. This tilt causes seasons. Summer occurs when a region gets more direct sunlight. Winter occurs when a region gets less direct sunlight. Near the equator, the amount of sunlight doesn't change much throughout the year, so it stays warm. But as you move toward the poles, the difference in sunlight between summer and winter becomes more noticeable, leading to bigger changes in temperature. Why is latitude important for temperature? Latitude is the most important factor in determining a place's climate because it directly affects how much solar energy, sunlight, a place receives. Isotherms are lines on a map that show places with the same average temperature. When we look at these lines, we see they usually run east to west, which shows that latitude has a big influence on temperature. Other factors affecting temperature. While latitude is the most significant factor in determining temperature, there are other factors that also play a role. 1. Altitude. Higher places, like mountains, are usually cooler because the air is thinner and holds less heat. 2. Proximity to water. Places near oceans or large lakes often have milder temperatures because water heats up and cools down more slowly than land. 3. Ocean currents. Warm or cold ocean currents can raise or lower the temperatures of coastal regions. 4. Cloud cover. Clouds can block sunlight and cool down an area, or trap heat and keep it warm, affecting the local temperature. Examples to understand latitude and temperature better. Equatorial regions. Cities like Singapore and Quito are near the equator. They receive direct sunlight all year, so they have a hot and humid climate. Polar regions. Places like Antarctica and the Arctic have very cold climates because they receive less direct sunlight. Temperate regions. Places like the United States or Europe experience more variation in temperature because they are located between the equator and the poles. They have 4 seasons: winter, spring, summer, and autumn. Altitude and temperature. How does altitude affect Earth's temperature? To understand how temperature changes with altitude, let's break down some important concepts. What is altitude? Altitude is how high something is above sea level. For example, a mountain's altitude is its height from the base, sea level, to the peak, top. As you go higher in altitude, you move away from the Earth's surface and into the atmosphere. How does altitude affect temperature? 1. Decrease in temperature with altitude. As you go higher in altitude, like climbing a mountain, the temperature decreases. This means it gets colder the higher you go. This cooling effect is mainly noticeable in the troposphere, which is the lowest layer of the atmosphere where most of our weather happens. 2. Why does temperature decrease with altitude? The Earth's surface is a major source of heat for the atmosphere. The surface absorbs sunlight and warms up, and then it warms the air directly above it. The further you go from the Earth's surface, the less heat there is to warm the air. This is why temperatures drop as altitude increases. 3. Normal lapse rate. The rate at which temperature decreases with an increase in altitude is called the normal lapse rate. On average, for every 1 kilometer, 1,000 meters, you go up in the troposphere, the temperature drops by about 6.5 degrees Celsius, 11.7 degrees Fahrenheit. 4. Air density and water vapor. The air near the Earth's surface is denser and contains more water vapor, dust, and other particles. These particles absorb and retain more heat, which keeps the lower atmosphere warmer. Higher up, the air is thinner, less dense, and contains fewer particles and water vapor, which means there is less material to absorb and hold onto heat. This makes higher altitudes colder. Examples to understand altitude and temperature. Mountain snowcaps. Even in warm regions near the equator, like Mount Kenya in Africa, the tops of tall mountains are cold enough to have permanent snow. Mount Kenya is about 5,199 meters, 17,057 feet high. Despite being near the equator, which usually means warm temperatures, the altitude is so high that temperatures drop enough for snow to remain year-round. Key points about altitude and temperature. As altitude increases, temperature decreases. This is true mainly in the troposphere, the lowest layer of Earth's atmosphere. Higher altitudes are colder because 1. They are further away from the heat source, Earth's surface. 2. The air is thinner and holds less heat. 3. There are fewer water vapor and particles to absorb heat. This is why mountaintops are often cold and snowy, even if they are located in warmer regions near the equator. By understanding these concepts, you can better understand why high-altitude places, like mountain peaks, are much colder than areas at sea level, even if they are in typically warm parts of the world. Why land and water heat up differently. When the sun shines, it sends energy to the earth in the form of sunlight, which is also called solar radiation. This energy heats up everything it touches, like land, water, or ice. But these different surfaces heat up and cool down in different ways. 1. Land heats up and cools down faster than water. Land heats up quickly when the sun shines on it and also cools down quickly when the sun goes away. Water, like oceans, lakes, and rivers, heats up more slowly and also cools down more slowly. Think about how sand at the beach gets hot very fast under the sun, but the water in the sea remains cool for much longer. This happens because land and water absorb and store heat differently. Reasons why land and water heat differently. There are several reasons why land and water do not heat up the same way. Transparency of water versus seeing opaque land. Water is transparent. Water is clear, which means sunlight can pass through it and spread out over a deeper area. This allows the heat to go deeper into the water. Land is opaque. Land is not clear. The sunlight only heats the top layer of the soil or rock, concentrating the heat in a small area, which makes the temperature go up more quickly. Example. Imagine a glass of water and a small piece of rock left in the sun. The rock will get hot on the surface very quickly, but the water in the glass will take longer to warm up. Specific heat of water is higher than land. Specific heat is the amount of heat needed to raise the temperature of a substance by 1 degree Celsius. Water has a high specific heat, which means it needs more energy to warm up compared to land. Water stores heat better. Because water needs more heat to increase its temperature, it warms up slower, but also holds on to that heat for longer. Land heats up and cools down faster. Land has a lower specific heat, so it takes less heat to warm up and also loses heat more quickly. Example, think about a metal spoon and a pot of soup on a stove. The metal spoon, like land, gets hot very quickly, but the soup, like water, takes longer to heat up and stays hot for longer. Water moves, land doesn't. Water is fluid and moves around. Water can flow and move, so when it gets heated on the surface, it mixes with cooler water below. This movement helps spread the heat through a larger volume of water. Land is solid and stays still. Land cannot move like water. Heat only spreads very slowly through the soil by conduction, so only the top layer gets heated up. Example, imagine stirring a pot of soup. The heat spreads evenly because of the movement. But if you just heat a solid object like a rock, only the part touching the heat source gets hot, while the rest remains cool. Evaporation cools water more than land. Evaporation is when water changes from a liquid to a gas. This process needs heat. When water evaporates, it takes away some heat from the water body, which cools it down. Water bodies evaporate more because oceans, lakes, and rivers have a lot of water. They have more evaporation. This cools them down, especially in summer. Land evaporates less. On land, evaporation only happens if the ground is wet, and only when the sun is shining. So land surfaces cool down less by evaporation. Example, think of sweating on a hot day. When sweat evaporates from your skin, it cools you down. Similarly, water bodies lose heat through evaporation, cooling them down more than the land. How these differences affect climate. Because land and water heat differently, this leads to different climates in different areas. Continental climates. Areas far from the sea, like the middle of a large continent, experience more extreme temperatures, hot summers and cold winters. This is because land heats up and cools down quickly. Marine climates. Areas near the sea have milder temperatures, cooler summers and warmer winters. This is because water heats up and cools down slowly, moderating the temperature changes. Example, think about cities like San Francisco near the ocean, which have mild weather all year round. In contrast, places like New Delhi, far from the ocean, have very hot summers and cold winters. Additional simplified points. Land versus water heating. Water acts like a big heat storage, slowly warming up and cooling down, while land reacts quickly, getting hot or cold much faster. Day and night temperature changes. Over land, temperatures can change a lot from day to night because land loses heat quickly. Over water, temperatures stay more stable because water retains heat. By understanding how land and water heat differently, we learn why the Earth has such a variety of climates, and why coastal areas often have milder weather compared to places far. What are ocean currents? Ocean currents are like giant rivers flowing through the ocean. They are large movements of ocean water from one place to another. These currents move to help balance or equalize temperatures across the planet. Warm currents. These currents flow from warmer areas, like near the equator, towards the colder polar regions. Cold currents. These currents flow from colder areas, like near the poles, towards the warmer equatorial regions. Why do ocean currents move? Ocean currents move to balance the Earth's temperature. They help transfer heat from warmer regions to colder ones and vice versa. This movement helps regulate the Earth's climate and weather patterns. How ocean currents affect climate. Ocean currents have a big impact on the climate of nearby land areas. Here's how. 1. Warm currents raise temperatures. Warm currents, like the North Atlantic Drift, carry warm water from the equator towards the poles. These currents warm the nearby coastal areas. For example, the warm North Atlantic Drift keeps the coasts of Great Britain and Norway warmer than they would normally be, even though these places are at high latitudes, closer to the North Pole. Because of the warm currents, winters in places like northwestern Europe are milder. The coastal areas do not freeze, and temperatures are higher than you would expect for such high latitudes. Example, London, which is located at 51 degrees latitude, has a mean average temperature in January that is about 4.5 degrees Celsius higher than New York City, even though New York City is at a lower latitude, 40 degrees. This is because the North Atlantic Drift brings warm water to the coast near London, keeping it warmer. Model 2. Cold currents lower temperatures. Cold currents carry cold water from the polar regions towards the equator. These currents cool the nearby coastal areas. For example, the cold California current along the western coast of North America keeps the coastal areas of Southern California cooler during the summer. The effect of cold currents is most noticeable in tropical areas or during summer months in temperate regions. Example, Walvis Bay, located on the coast of Namibia in Africa, 23 degrees east latitude, is cooler than Durban, which is further south at 29 degrees C, due to the Benguela cold current flowing near Walvis Bay. This cold current lowers the temperature of the surrounding area. Examples of how ocean currents affect local climates. 1. North Atlantic Drift, warm current. Location, North Atlantic Ocean. Effect, keeps northwestern Europe warmer in winter than other places at similar latitudes. For instance, despite its northern location, Great Britain does not have freezing winters because the warm current raises the temperature of the coastal waters. Number 2. California current, cold current. Location, along the western coast of North America. Effect, keeps the summer temperatures of Southern California lower. This is why places like San Francisco and Los Angeles have cooler summers compared to inland areas of the same latitude. 3. Benguela current, cold current. Location, off the west coast of southern Africa. Effect, cools down coastal areas like Walvis Bay, making them cooler than places further south like Durban, which do not feel the effects of the cold current as much. Why are ocean currents important? Climate regulation. Ocean currents help regulate the Earth's climate by moving warm and cold water around. This makes some regions warmer or cooler than they would otherwise be. Weather patterns. Currents also affect local weather patterns, bringing rain to some places and dry conditions to others. Marine life. They help in the distribution of nutrients, which supports marine life. Cold currents are rich in nutrients, supporting fisheries and marine ecosystems. Conclusion. Ocean currents play a crucial role in shaping the climate and weather of coastal regions around the world. By moving warm and cold water to different parts of the globe, they help balance temperatures, which in turn affects the climate and living conditions of nearby land areas. Understanding how these currents work better predict and prepare for weather changes and understand the Earth's climate system. What are prevailing winds? Prevailing winds are winds that blow predominantly from a single general direction over a particular point on the Earth's surface. These winds can have a significant effect on the climate and temperatures of the regions they blow across, especially in coastal areas. How prevailing winds affect temperature. 1. Onshore winds. These are winds that blow from the ocean towards the land. Moderating effect. When winds blow from the ocean onto the land, they carry the temperature moderating effects of the ocean with them. This means that the warm or cold ocean currents can affect the coastal climate. For example, warm ocean currents like the Gulf Stream can bring warmer air to coastal regions, while cold currents can cool down the coastal areas. 2. Offshore winds. These are winds that blow from the land out towards the ocean. Reduced influence. When winds blow from the land to the ocean, they carry away the moderating effects of the ocean. This means that the coastal areas will not feel the temperature influence of the ocean as much. Warm or cold currents won't have as much impact on the land if the prevailing winds are blowing in the opposite direction. Example: in the winter, if the winds are blowing from the ocean to the land, the warmer air from the ocean can help keep the coastal areas milder. However, if the winds are blowing offshore, from land to sea, the coastal areas can become colder because they are not receiving the warm air from the ocean. What is cloudiness? Cloudiness refers to the amount of cloud cover in the sky. Clouds play a major role in regulating the temperature of the Earth's surface and atmosphere. How cloudiness affects temperature. 1. Daytime temperature, less cloud cover. In areas with clear and cloudless skies, more solar radiation reaches the Earth's surface. This means places like deserts can get extremely hot during the day because there is nothing to block or absorb the sun's rays. More cloud cover. In regions with heavy cloud cover, such as near the equator, clouds block a portion of the incoming solar radiation. This reduces the amount of heat reaching the surface, resulting in cooler daytime temperatures compared to regions with less cloud cover. Number 2, nighttime temperature. Cloudy nights. At night, clouds act like a blanket. They trap heat that is being radiated from the Earth's surface, keeping the temperature warmer. This is why humid, cloudy regions often have warmer nights than arid, cloudless regions. Clear nights. In places with clear skies at night, there is nothing to trap the heat being radiated from the Earth's surface. This allows the heat to escape into space, leading to cooler nighttime temperatures. How cloud cover moderates temperature. Moderation effect. The general effect of cloud cover is to moderate temperatures. Lower daytime highs. Thick cloud cover reduces the amount of sunlight insolation reaching the Earth's surface, which lowers the potential maximum temperature during the day. Raise nighttime lows. At night, clouds help to retain heat, which raises the potential minimum temperature. Example: in subtropical deserts like the Sahara, clear skies allow for intense heating during the day, but also rapid cooling at night. In contrast, in a humid region like the Amazon rainforest, the daytime temperatures are lower than in deserts due to cloud cover, and nighttime temperatures are higher because clouds retain the heat. Conclusion: both prevailing winds and cloudiness play crucial roles in regulating temperatures on Earth. Prevailing winds determine whether the moderating effects of ocean currents are felt on land, while cloud cover regulates how much sunlight reaches the Earth and how much heat is retained. Understanding these factors helps explain why different regions have different climates and temperature patterns. Understanding mountain barriers and their impact on climate. Mountain barriers refer to high mountain ranges that can significantly affect the temperature and climate of an area. These barriers influence the movement of air, acting as shields that block or redirect wind and weather patterns. This can create distinct climatic differences on either side of the mountain range. How mountain barriers affect temperature. 1. Blocking cold air. Mountains can prevent cold air from moving into certain regions. Example: the Himalayas. The Himalayas are a high mountain range that runs across northern India. They act as a barrier that blocks cold air from Central Asia during the winter. Because of this, the Indian subcontinent, south of the Himalayas, remains warmer in the winter than it would if the cold air could move freely into the region. 2. Blocking warm air. Mountains can also block warm air from reaching certain areas. Example, the Alps. The Alps run east to west across Europe and act as a barrier to cold polar winds from the north. This means that the areas to the south of the Alps, like northern Italy, are protected from extremely cold air masses, keeping their temperatures higher than they would be without the mountains. 3. Directing winds and weather patterns. Mountains can force winds to go around them or over them, changing weather patterns. Example, the Rockies. The Rocky Mountains in North America act as a barrier to moisture-laden winds from the North Pacific Ocean. This means that moist air is blocked, leading to less rainfall on the eastern side of the Rockies, known as the rain shadow effect. Meanwhile, the Rockies do not block cold polar air from moving southwards, which can cause cold spells in the southern United States. The rain shadow effect. The rain shadow effect is a dry area on the leeward side, the side sheltered from the wind, of a mountain range. Here's how it works. 1. Windward side. As moist air blows in from the ocean and reaches a mountain range, it is forced to rise. As the air rises, it cools and condenses, leading to precipitation, rain or snow, on the windward side of the mountain. This side tends to be lush and green. Leeward side. After the air has released most of its moisture on the windward side, it crosses over the mountain peak and descends on the leeward side. As it descends, it warms up, leading to dry conditions. This side of the mountain is often much drier and is where deserts are commonly found. Example, the Atacama Desert in Chile. The Andes Mountains block moist air coming from the Atlantic Ocean, creating a rain shadow effect on the west side, leading to the formation of one of the driest deserts in the world. Why mountains create different climatic regions. Mountains act as natural barriers, creating different climates on either side due to blocking air movement. They stop certain air masses, warm or cold, from passing through, influencing local temperatures. Creating rain shadows. They cause precipitation on one side and dry conditions on the other, leading to varying amounts of rainfall. Altering wind patterns. They force winds to change direction, affecting how and where the weather patterns move. Conclusion. Mountains are powerful natural features that shape climates by blocking or redirecting air and moisture. Whether protecting regions from cold air, creating deserts, or influencing rainfall, they play a critical role in defining the weather and climate of different areas on Earth. Understanding their influence helps us comprehend why some areas are dry and desert-like, while others are lush and green, even when they are relatively close to each other. Understanding relief and its impact on temperature. Relief refers to the variations in elevation and slope of the land surface. It plays a significant role in determining local temperatures by influencing factors such as insolation, incoming solar radiation, radiation loss, and air movement. Here's how relief affects temperature. 1. Elevation and temperature. Higher elevations and temperature. At higher elevations, even though there is more insolation because the air is thinner and less cloudy, there is also a greater net loss of heat, terrestrial radiation. The reason is that the lower density of air at high elevations absorbs less of this radiation. This means that although higher elevations receive more solar energy during the day, they lose heat more rapidly at night, leading to greater temperature variations. No generalization for high elevations. The impact of elevation on temperature cannot be universally applied, as high elevations often have more cloud cover, which can complicate temperature effects. Clouds can reflect solar radiation during the day, reducing temperatures, and trap heat at night, preventing rapid cooling. Slope, orientation, and insolation. Effect of slope on sunlight. The orientation of a slope, the direction it faces, affects how much sunlight it receives. In the northern hemisphere, slopes facing south receive more direct sunlight for a longer duration compared to north-facing slopes. This leads to southward slopes, warmer due to prolonged sunlight, making them more suitable for human settlements and agriculture. Northward slopes, cooler and often covered with forests because they receive less direct sunlight. Effect on alpine valleys. In mountainous regions like the Alps, settlements are typically located on southward-facing slopes where there is more warmth and light for agriculture and habitation, while north-facing slopes remain forested and less developed. 3. Cold air drainage and temperature inversions. Cold air drainage. In hilly areas, cold, dense air tends to flow down the slopes and settle in the valleys. This phenomenon can cause the valleys to be colder than the surrounding higher ground. This process can lead to a temperature inversion, where temperatures increase with altitude instead of decreasing. Normally, as you go higher in altitude, the temperature drops. However, due to the accumulation of cold air in valleys, the valleys may be colder than the slopes above. Impact of temperature inversions. Killing frosts in valleys. These inversions can cause frost in valleys where temperatures drop below freezing, while the higher slopes remain above freezing. This can be detrimental to crops and vegetation in the valleys. Conclusion. Relief plays a crucial role in local climate and temperature variations due to its influence on solar exposure, heat retention, and air movement. Higher elevations tend to have greater temperature extremes due to higher insolation and rapid heat loss. Slope orientation affects the amount of sunlight received, influencing human activity and vegetation patterns. Cold air drainage can create temperature inversions, leading to colder conditions in valleys compared to the surrounding slopes. Understanding these dynamics is essential for predicting local weather patterns, planning agriculture, and managing natural resources in hilly and mountainous regions. Sure, let's break down how convection and turbulence affect temperature in a simple way. What are convection and turbulence? Convection is when warm air rises and cool air sinks. This movement helps spread heat in the atmosphere. Turbulence involves small, swirling movements of air that mix warmer and cooler air together. Both processes help balance temperatures in different parts of the atmosphere and on the ground. 1. Convection currents. How do they work? During the daytime, the sun heats the Earth's surface. The ground then warms the air that is close to it. Warm air is lighter than cold air, so it starts to rise. As the warm air rises, it carries heat away from the surface to higher parts of the atmosphere. When the warm air rises, cooler air from above comes down to replace it. This movement of air is called a convection current. Example, imagine a pot of water on a stove. When the water at the bottom gets hot, it rises, and cooler water from above sinks. The same process happens in the atmosphere with air instead of water. 2. Turbulence, mixing air. Turbulence is like small whirlwinds or swirling air movements. It happens when the wind blows over rough surfaces like mountains, hills, or forests, or when the surface of the Earth heats up unevenly. These swirling motions mix the air, combining warm air with cooler air, which helps spread heat more evenly. Number 3. Winds and mountain effects. Foehn and Chinook winds. Sometimes winds blow over mountains and come down the other side. When this happens, the air that comes down the other side gets compressed, squeezed, which makes it warmer. These warm winds are called Foehn winds in Europe over the Alps and Chinook winds in North America over the Rockies. Effect of these winds. Foehn and Chinook winds can quickly raise the temperature of the areas they blow over. For example, in winter, these winds can cause the snow to melt fast and make the weather surprisingly warm in a short time. Number 4. Why convection and turbulence are important. Both convection and turbulence help balance temperatures. They spread heat around, so no single place gets too hot or too cold. Convection currents help transfer heat from the Earth's surface to the atmosphere. Turbulence mixes air of different temperatures, helping to moderate temperatures in specific areas. 5. Other factors that affect temperature. The temperature of a place isn't just about how far it is from the equator, its latitude. Other things like mountains, winds, ocean currents, and even how the Earth rotates around the sun also affect temperature. All these factors together create the different temperatures we experience in different parts of the world. Summary. Convection and turbulence are natural processes that help move heat around the atmosphere. They prevent any one area from getting too hot or too cold, making our climate more balanced and livable. They work together with other factors like winds, mountains, and ocean currents, the climate and temperatures we experience every day.